Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss the concept of normal distribution. If you have a set of observations, you can see how frequently does an individual value occur within the set. I have shown here the values of systolic blood pressure observed from a group of patients coming to my clinic. You can see that the normal value 120 occurs more commonly than other values. The extremes, such as 160, are relatively less frequent. To better visualize this, you can plot the frequency in y-axis and the individual values in x-axis. The unit of measurement here is millimeter mercury. You will then get a histogram, just like this. Jotting a curvy line across the top of all bars will give you a frequency distribution curve. Now if you draw a vertical line through the center, both sides of this curve will look the same. This curve is symmetrical. In addition, this curve has only one peak that lies on the most frequently occurring value, which is the mode, 120 here. Let us now calculate the mean, median, and mode for this dataset. These three values capture the central tendency of any dataset. As you can see, there are 38 observations in total. Mean is given by the sum of all values divided by the sample size. I've done this calculation here, and the value is 120. The most frequently occurring value is the one with the tallest bar. It is the mode, and this is 120. Median is the centralmost value, that is the average of 19th and 20th values. And in this case, as there are totally 38 observations, the average of 19th and 20th value, both of them being 120, gives you 120. So, in this particular data set, mean is same as the median and it is same as the mode. A set of observations is said to be normally distributed if the frequency distribution curve is symmetrical around a single peak, and if the mean is same as the median and the mode. In this case, there is no skew. Skew refers to the difference between mean and the median. In fact, this is indeed true for any biological continuous measurements that you take from the population. For example, most people will have normal average levels of cholesterol, but a few will have too high and a few too low levels. Same can be said for measures such as glucose levels, IQ, mood scores, etc. An important but not the only determinant of whether your data is normally distributed or not is the issue of sampling. If you have taken a large enough sample to represent the population, you can expect to see normality. This notion is called central limit theorem. The rule of thumb is to gather at least 30 people. So the central limit placed on normality is the sample size. If a data set is normally distributed, then its frequency distribution curve can be easily reconstructed using just two values, mean and standard deviation. I said you can reconstruct a normal distribution, a frequency distribution curve with two values, mean and standard deviation. How is this possible? We can rewrite the x-axis of the frequency histogram. Let us replace the actual observed values in terms of mean and standard deviation units. So instead of plotting blood pressure in terms of millimeters of mercury, I'm going to now plot the blood pressure observation shown in the previous example in terms of standard deviation units. How do I do this? As you can see, the mean is at the center, which corresponds to the value of 120. The other lower values such as 100, 80, etc. can be obtained by subtracting certain number of standard deviation units from the mean. These will be shown on the left. Similarly, higher values can be obtained by subtracting certain number of standard deviation units by adding certain number of standard deviation units to the mean, these values will be on the right. So instead of depicting the histogram with the actual observations, I have now redrawn the histogram in terms of mean and the amount of standard deviation units from the mean. A value is less or higher. As you can see, you get the same curve when you use the actual observed values or when you use the standard deviation units in the x-axis. An important utility of using standard deviation units is that if your data is normally distributed, then there are always a fixed number of people who score between two given values in standard deviation units. This curve is a perfect normal distribution curve. The tails of the curve reach close to x-axis but never touches it. As you can see in this curve, between mean and one standard deviation, 34.13% individuals fall. Between +1 and -1 standard deviation values, you will have 34.13 plus 34.13, which gives you 68.26%. So these numbers are fixed for any type of data collected, as long as it is normally distributed. Furthermore, as the curve is symmetrical, we can calculate the proportion scoring between any two values after converting these values in terms of mean and standard deviation units. So you can see -1 to +1 SD, 68.26% of people fall. Between -2 and +2 SD, around 95% of people fall. Between -3 and +3 SD, 99.6% of people would fall. You can standardize a normally distributed dataset by subtracting the mean and dividing the remaining values by standard deviation. In this case, you will get a standard normal distribution plot, z-plot. For the z-plot, the center is at 0 and the deviation along x-axis is 1 unit. The plot shown here is a z-plot, the standard normal plot. You can see the center point is 0 and along the x-axis the unit of calibration is 1. This refers to standard deviation of 1. Skew refers to the difference between mean and median. Normally distributed data has no skew. Positive skew means that the mean is higher than the median. This occurs if there are a lot of outliers with higher than average values in a sample. Negative skew means that the mean is lower than the median. This occurs if there are a lot of outliers with lower than average values in a sample. As you can see in these figures, the tails of a skewed distribution are unequal, not symmetrical. The direction of the longer tail gives you the direction of the skew. So if the right tail is longer, outliers have higher value, representing a positive skew. If the left tail is longer, outliers have a lower value, representing a negative skew. Transformation refers to a set of mathematical operations using which you can reduce the skewness within a dataset. You can transform skewed data by taking square root of all values, cubic roots of all values, inverse, logarithm of values, etc. There is no guarantee that these mathematical transformations will provide normal data upon transformation. We need to check for normality once again in the transformed data. If normality is still elusive, we should resort to non-parametric statistical tests when testing for significance of an effect. Look at this histogram. Is there a skew? If there is one, in what direction is it? As you can see, there are a lot of high age values present as outliers, while the median and probably the mode value is also on the lower end. So this is a positive skew. Now it's time to ask yourself a few questions. Sorry for the spelling mistake. It should say how will the distribution look like. Thank you for choosing SPMM course for your revision.